Hello YouTube. Today we're going to be talking about confidence intervals for statistics. We're going to be talking about how to find the mean and how confident you are in your values. You can generally have 95% confidence kind of range, or a 90%, depends how you want to approach it. But I'm just going to go over what these notations kind of means and what you're really doing when you're searching for confidence intervals. So here's an example just found out of a book. So you have a bunch of population of monarch butterflies, and you measure their wing area in centimeters squared, and they give you this small sample of this large population. They only take 14 butterflies, and they give the sample mean and sample standard deviation. So I took that information, wrote that down, pretty much the gist. So the sample size n is 14. Our y bar, which is our mean for the sample, is given, and our standard deviation is 2.48 centimeters squared. Now the reason why that's not sigma is because this is of a sample, so this is not the true standard deviation. So this is how we're going to figure out how to get that. If you had to pick from your sample what the average value of the area for the wingspan or for the wings of the butterflies, if you had to pick, knowing what you had, you would obviously guess that your mean is what your sample mean would be. So you're saying that, okay, my sample mean, since I got about 33 centimeters squared, I'm guessing that the entire population has an average of 33 centimeters squared as well. That's something called a point estimate, where you're given where you have an exact point where you think it's got to be this. You're just saying a number. Now, confidence intervals say, I think it's between 31 and 34, for example. That's giving an interval, but now you want to know how confident you are in that interval. So what we're doing is estimating to see how close we are from our sample to our population. Now, going back to the standard deviation before we go any further, that's if you want to convert your sample mean or your sample data into a better estimate about the population, you do something involving standard error. And standard error is the standard deviation of the sampling distribution for this particular statistic, and that can be shown in this formula. So your sample standard deviation over the square root of the sample size. Again, we don't use sigma over the square root of n for this case because we don't have the standard deviation for the entire population. This is, again, just a sample, and we're estimating the population from the data that we have. That's what sampling statistics here is what we're trying to use for. So again, that standard error is the standard deviation. So from the values given, you simply plug in those values, and you get your population standard deviation to be 0.66 centimeters squared. Now, pretty much what we did here was say, is our sample mean reliable? Now we're trying to figure out, is our sample mean truly reliable to estimate the mean of the entire population? Well, our sample size is really small, so it doesn't really quite look like it. So how reliable is our data? So we can use our sample mean and standard deviation to estimate the population and get more information about it. So this interval of convergence that we're going to talk about, you can lose its precision but gain probability. So you might not, the actual population might be 32.81 centimeters squared, but it's very unlikely, since your sample size is small, that that is true. So, but for some reason, if you miraculously were right, then that would be excellent precision because you got it down. But when you strain an interval, you have a better chance of getting it right, or a greater probability of finding the correct answer. You can compare the interval of convergence, the confidence interval, and the point estimate versus, compare it to like a shotgun or a rifle. So if you have a sniper rifle, that's a point estimate. You're shooting exactly for 1 point. But if you have a shotgun, the bullets can go anywhere and they can hit the target. And you have that confidence range. If you want to go less violent analogy, you could do a fishing pole where you only can catch one fish versus a fishing net where you have a wider range. So now we're going to go into an example of what we mean by this confidence interval. So if we have a very large sample confidence interval, for the case of this argument, let's just say our sample size is 1,139, and we'll consider that large. And the sample mean is 145.3, and the standard deviation of that sample mean is 12.87. We want to know that confidence interval to be at 95% in our answer. So we're trying to say, does our mean fall in 95% chance of getting it right? You want to be that confident in your answer. So we use this formula to calculate the confidence interval. So it's the sample mean plus or minus z alpha over 2 times the standard error, which is the sample mean over the square root of the sample size. So this may seem daunting, but we're just going to break it down a little bit. So alpha pretty much is what we're not confident about. So it's pretty much 1 minus your percent confidence interval. So we're 5% not confident about choosing the wrong answer. So simply divide that by 2. So that's, again, doing the calculations for this one. So it would be 1 minus 0.95, which is 0.05, or 5%. And that divided by 2 is 0.025, or 2.5%, when using the formula. Now, z you're probably familiar with if you're talking about standard normal curves and converting standard normals or just normal distributions into standard normal distributions. Simply acquiring your z value, which if you don't know more about this, I have a video on that. You can check that out. But then you'd produce a graph something like this. So what you were doing is you were looking for since this is a symmetric curve, 0.025 on both sides. So that means using this curve here, I looked for something that would add up to 50 minus 2.5. So 50 minus 2.5 would be about 47.5. So I looked for that here on the table and acquired my z value, which is 1.96. And I got that value there, and that would be both on the positive end and the negative end, since this is symmetric. And then you simply use the formula. So we have our y bar, which is given, and then you do plus or minus our z value, which we calculated using the table, the z table, and multiply that by our standard error, and you get this as your interval of convergence. You can convert that into numbers to actually get the actual values. Say I am 95% confident that the sample mean, or that the actual mean of the population is between 114.55 and 114.605. So that just mathematically proves that you're 95% confident that the mean falls between those points. Okay, so now I want to talk about this formula here. But before I do that, let's say we wanted to calculate a 90% confidence limit instead of 95. So we'll use the same stuff. So again, your alpha is what we're not confident about. So that'd be 1 minus 0.9, which is 0.1. Alpha divided by 2 would be 0.05, and our z alpha over 2 would be using the would be 1.645. And again, you would have to use your z table. You would look at 0.45 to get your value, which is 1.645. That's how we got our z alpha over 2 value. And again, using this formula, you plug in the numbers and you get your confidence interval. So let me ask you, what was different? Z alpha over 2 was the thing that changed. And we got closer to our value, our mu, but we were less confident in our answer. And since this interval is smaller than our 95% confidence limit, if you notice, then we have a less probability of getting the correct or the perceived mu, or the mean. So now with that in mind, we're going to analyze this formula here and see what we would do if we could change the values. So if the sample size increases, what would happen? Well, if sample size increases, the denominator is going to get really, really big. So that means our interval would get really, really small. Since you're multiplying by a fraction pretty much. So the larger you have of a sample size, your interval decreases, and you're more and more confident, and you could be more and more confident in your answer. And then if your standard deviation gets really, really big, what happens? Your interval will decrease as well, because the numerator is going to get really, really big, excuse me, that's not correct. I'm thinking now. It would actually get really, really big as well. Because again, it's in the numerator. See, I made a mistake. You just got to talk it out and you figure out why. And the reason why I caught my mistake, or how I figured it out, was if the numerator is getting really, really big, you're going to multiply by a super large number, so that means the interval is going to increase as well. Now, does y have any impact on the interval of confidence interval? Well, yes and no, but it's mostly just a matter of where your confidence interval begins. It's not going to shift it anywhere or anything. It's just going to be like, well, where is it? Like, what number are you talking about? So there's really no true effect on it, but it just shows a matter of location. So I hope this helps with with confidence intervals, and relating it to how you take a sample and you want to statistically analyze how it relates to the population. Hope this helps.